Imagine this: you wake up tomorrow to find the sun has seemingly vanished. The sky remains dark well past dawn, temperatures begin to drop, and panic spreads across the globe. Yet remarkably, life continues. Plants still photosynthesize, albeit at reduced rates. Animals adjust their behaviors. And humanity, though facing unprecedented challenges, finds ways to adapt and survive. This scenario is not mere science fiction. It represents a fascinating intersection of solar physics, atmospheric science, and biological resilience that reveals surprising truths about our star and our own adaptability. The Sun, our 4.6 billion-year-old stellar companion, is not the immutable, eternal furnace we often imagine. Like all stars, it experiences fluctuations and cycles that scientists have studied for centuries. In 1843, amateur astronomer Samuel Heinrich Schwabe first documented the roughly 11-year sunspot cycle after 17 years of daily observations. This discovery revealed that our star experiences regular periods of heightened and diminished activity. But what if something far more dramatic than a typical solar minimum were to occur? People often assume the sun is unchanging, but that is far from true, explains Dr. Melanie Barton, solar physicist at the High Altitude Observatory in Boulder, Colorado. We have documented evidence of extended periods when solar activity dramatically decreased, with profound effects on Earth. The most famous of these periods, the Maunder minimum, lasted from approximately 1645 to 1715. During this 70-year span, sunspots became exceedingly rare. Astronomers of the era, including Giovanni Cassini and Johannes Hevelius, recorded fewer than 50 sunspots over decades, compared to the thousands typically observed during comparable periods. Simultaneously, Europe experienced unusually cold winters, with the Thames River in London regularly freezing solid enough to support frost fairs, complete markets and festivals held on the ice. What makes the Maunder minimum particularly interesting, continues Dr. Barton, is that it coincided with the Little Ice Age, when average global temperatures dropped by approximately 1 to 1.5 degrees Celsius. While the cooling had begun before the solar minimum and continued after it ended, the overlap suggests a potential connection between solar activity and Earth's climate. But could the sun actually go dark in a more dramatic fashion than the subtle dimming associated with the Maunder minimum? Remarkably, the answer is yes, at least from our perspective on Earth. In 2012, NASA's Solar Dynamics Observatory captured footage of a solar filament, a massive, snaking structure of plasma held aloft by magnetic fields erupting from the sun's surface. The eruption sent a coronal mass ejection, CME, hurtling through space. Had this powerful eruption occurred just 1 week earlier, Earth would have been in its direct path. That 2012 event was a wake-up call, says Professor Brian Jensen, astrophysicist at the University of Michigan. Our calculations indicate that had it hit Earth, it would have been comparable to the Carrington event of 1859, possibly even stronger. The Carrington event, named after British astronomer Richard Carrington who observed the associated solar flare, remains the most powerful geomagnetic storm in recorded history. It generated auroras visible as far south as Cuba and caused telegraph systems across North America and Europe to fail, with some operators reporting sparks flying from their equipment. What many people do not realize, Professor Jensen continues, is that extremely powerful solar storms could potentially trigger a sequence of events that would make the sun appear to go dark from our perspective, even though the star itself would remain active. The mechanism for this seemingly impossible scenario lies in Earth's magnetosphere and atmosphere. When a sufficiently powerful CME strikes Earth's magnetic field, it can compress it dramatically on the day side and stretch it on the night side, creating what scientists call a magnetospheric reconfiguration. During the most extreme events, this reconfiguration can trigger massive electrical currents in Earth's ionosphere, the layer of our atmosphere that extends from about 50 to 600 miles above the surface. These currents, in turn, can heat the atmospheric gases to the point where they undergo significant chemical changes. Research published in the journal Atmospheric Chemistry and Physics in 2018 by a team led by Dr. Catherine Marshall revealed that intense solar storms can cause nitrogen and oxygen in the upper atmosphere to form nitrogen oxides, NOx, and other compounds that are efficient at absorbing certain wavelengths of sunlight. In our simulations of extreme solar storms, Dr. Marshall explained, the production of these compounds could create a temporary but significant atmospheric opacity that would filter substantial amounts of sunlight before it reaches the surface. This filtering effect would not block all light. It would not be like a total solar eclipse, but rather it would significantly dim the sun's appearance and alter the color and quality of the light that reaches Earth's surface. The sun might appear dramatically darker, reddish, or even take on a strange purplish hue depending on the specific atmospheric chemistry involved. Historical records provide tantalizing hints that such events may have occurred in the past. In 774 to 775 CE, tree ring data shows a spike in carbon-14 that suggests an extremely powerful solar event, possibly 10 to 100 times stronger than any recorded in modern times. Chronicles from the period mention unusual atmospheric phenomena, including a strange fog and diminished sunlight that lasted for periods ranging from days to weeks. Similar accounts appear in historical records from 993 to 994 CE, corresponding to another carbon-14 spike in the tree ring record. Japanese observers described the sun as appearing tarnished and as if veiled by thin clouds even on clear days. How long could such a solar dimming last? According to atmospheric scientist Dr. Thomas Robinson, the persistent effects would likely last from days to perhaps 2 weeks in the most extreme scenarios. The atmospheric chemistry would gradually return to normal as the compounds are broken down by photochemical processes and the air circulates. But what about the survival aspect? How would life on Earth cope with a temporarily darkened sun? The answer lies in the remarkable resilience of Earth's ecosystems and the adaptability of human society. Unlike a sudden extinction-level event like an asteroid impact, a solar dimming would be gradual enough to allow for adaptation. Plants, the foundation of terrestrial food webs, are surprisingly tolerant of reduced light conditions in the short term. Dr. Elena Sanchez, a botanical physiologist at the University of California, Berkeley, explains, most plant species can maintain basic metabolic functions for weeks under significantly reduced light conditions. While growth and reproduction might slow or pause, the plants themselves would not immediately die. Indeed, research on the aftermath of volcanic eruptions provides a natural analog for understanding biological responses to reduced sunlight. Following the 1991 eruption of Mount Pinatubo in the Philippines, global temperatures dropped by about 0.5 degrees Celsius for nearly 2 years as volcanic aerosols in the stratosphere reflected solar radiation back into space. Yet agricultural systems, while affected, did not collapse. The marine ecosystem might actually experience some short-term benefits. Phytoplankton are exquisitely sensitive to light levels, explains marine biologist Dr. James Patterson. A moderate reduction in sunlight could actually increase productivity in species currently experiencing photoinhibition, essentially sunburn at the cellular level, in the upper ocean layers. For humans, the challenges would be significant but surmountable, especially in the modern era. The most immediate effect would be psychological. The profound disorientation of a darkened daytime sky would trigger anxiety and fear. Yet this very darkness would make the situation self-evident, allowing authorities to communicate the temporary nature of the phenomenon. Energy systems would face strain but not collapse. Solar power generation would decrease dramatically, but other sources, hydroelectric, wind, nuclear, and fossil fuels, would continue functioning. Modern power grids are designed with redundancy specifically to handle fluctuations in supply and demand. Temperature decreases would be gradual rather than sudden. Earth's oceans, which cover 71% of the planet's surface, serve as an enormous heat sink. Their thermal inertia means they release stored heat slowly, moderating temperature changes. During the Maunder minimum, average temperatures dropped by about 1 to 1.5 degrees Celsius over decades, not days or weeks. The biggest challenge would be managing the human response, notes sociologist Dr. Martha Blackman, who studies crisis management. Panic and misinformation could potentially cause more harm than the actual physical effects of the event. Government agencies are not unaware of these risks. In 2014, the White House Office of Science and Technology Policy released the National Space Weather Strategy and Action Plan, which includes contingencies for extreme solar events. Similarly, the International Space Environment Service coordinates global monitoring of solar activity and provides alerts about potential disruptions. Perhaps most surprisingly, such an event might ultimately strengthen rather than weaken human society. Historical analysis of communities affected by natural disasters often shows an increase in social cohesion and cooperative behavior during the recovery period. Psychologists call this the therapeutic community effect, a temporary suspension of normal social divisions in favor of collective action toward recovery. Dr. Blackman adds, shared experiences of survival and adaptation often become defining moments for cultural identity and technological development. The brief darkening of the sun might ultimately accelerate certain innovations, particularly in energy independence and local food production. The scientific understanding of these solar phenomena continues to evolve. In 2025, NASA and the European Space Agency plan to launch the Solar Orbiter, a mission designed to observe the sun's poles for the first time. This unprecedented view may reveal previously unknown aspects of solar dynamics and improve our ability to predict extreme solar events. Meanwhile, the Parker Solar Probe, launched in 2018, has already made history by becoming the first spacecraft to touch the sun, flying through the corona and directly sampling particles from our star. Data from this mission is revolutionizing our understanding of solar wind acceleration and the mechanisms behind coronal mass ejections. Every new discovery about the sun reveals how much more there is to learn, reflects Professor Jensen. We have moved from seeing it as a simple nuclear furnace to understanding it as a complex, dynamic system with behaviors we are only beginning to predict. This scientific journey reveals a profound truth: the apparent stability of our natural world often masks remarkable dynamism and change. The sun, seemingly eternal and unchanging to human perception, undergoes constant fluctuation. Earth's atmosphere, invisible in our daily experience, serves as both vulnerability and protection. And life itself demonstrates resilience through adaptation rather than through immutability. Should the sun appear to go dark tomorrow, it would not signal the end of the world, but rather would illuminate the complex, interconnected systems that sustain life on our planet. It would remind us that survival does not depend on stability, but on resilience, the capacity to absorb change while maintaining essential functions. Perhaps this is the most important lesson of all: in a universe defined by change, adaptation is not just a biological strategy but a cosmic necessity. We survive not because our environment remains constant, but because life itself embodies the capacity to transform constraints into opportunities. And so, in the temporary darkness of a dimmed sun, we might discover not just the remarkable physics of our star and atmosphere, but the even more remarkable adaptability that defines life on Earth, including our own.